Hello everyone, my name is Hyunglae Lee and I'm a director of the Neuromuscular Control and Human Robotics Lab at ASU. First, I'd like to thank all the workshop organizers for inviting me to this exciting workshop. In this presentation, I'll briefly share our recent efforts to develop a biomechanics-based variable damping controller to enhance physical-human-robot interaction. Robotic arm manipulators that physically interact with humans have gained high popularity in many settings, for example, industrial settings and clinical applications. When controlling physically interactive robots, including robotic arms, it is critical to build a control system that guarantees stable and safe physical interaction without neglecting or sacrificing performance. Addressing the trade-off between agility and stability has been a very important issue in the history of physical-human-robot interaction. In order to guarantee safety and stability in physical-human-robot interaction, current research has been focused on building energetically passive or dissipated robots. While this approach guarantees coupled stability and safety of the human-robot system, this conservative design sacrifices agility and transparency in physical-human interaction. In this study, we introduced a biomechanics-based variable damping controller with a goal to improve this trade-off. The basic concept of the biomechanics-based variable damping controller is to change the damping component of a robotic impedance or admittance controller over a wide range of damping values, mainly based on human users' damping properties and users' intent on movement. Unlike typical robotic controllers imposing positive damping, the proposed controller utilizes both positive and negative damping values. Given the fact that the human neuromuscular system exhibits dissipative behavior during physical interaction, we could impose negative robotic damping to some extent without compromising the coupled stability of the human-robot system. In other words, robotic damping can be negative as long as damping of the coupled human-robot system is positive. Another important factor in the variable damping controller is user's intent on movement. When the user intent is to accelerate and move, negative robotic damping will be imposed to improve agility. And when the user intent is to decelerate and stop, positive robotic damping will be imposed to improve stability. For successful realization of the variable damping controller, it is critical to identify the degrees of human damping modulation during physical-human interaction. However, compared to extensive studies on arm stiffness, arm damping or viscosity has been relatively understudied. This is partly due to technical challenges in estimating the damping component of the human arm impedance. For example, quantification results of arm damping is highly sensitive to different estimation methods. Limited knowledge on how human arm damping is modulated during physical interaction limits its application to robotic controllers. In order to overcome the limitation of directly quantifying arm damping, we use an alternative approach. If lower bounds of robotic damping that humans can stably interact with are known, the impedance controller could utilize a wide range of robotic damping even without directly quantifying human arm damping. So we investigated human arm stability during interaction with a robotic arm, simulating unstable, damping-defined mechanical environments, and identified the lower bounds of robotic damping that humans can stably interact with. We performed human experiments using a robotic arm simulating negative damping-defined mechanical environments and investigated kinematic stability of the arm at each experimental condition. From our pilot study, we learned that humans have a higher capacity to stabilize the arm along the anterior-posterior direction than the medial-lateral direction, which is consistent with previous arm impedance studies. Based on this prior knowledge, we manipulated the admittance controller of the robotic arm such that it simulated more challenging environments in the AP direction than the ML direction. The experiment was focused on the horizontal plane, and zero stiffness was simulated in this plane. While human subjects were interacting with different damping-defined environments, the robotic arm applied rapid position perturbations to disturb arm posture and challenge its stability. We performed the experiment with varying perturbation profiles and inertia values to evaluate their effects on the arm stability. Here are representative trials of the arm stability experiment in the AP direction. We first provided two small targets around the home position and instructed the subject to hit those targets. This allowed the subject to explore negative damping defined mechanical environments. When the arm came back to the home position, the robot applied fast position perturbation after a short random pause period, and the subject was instructed to maintain stable arm posture at the home position. When the magnitude of negative robotic damping was not large, subjects could stably interact with the robotic arm, applying external perturbations. However, as the magnitude of negative robotic damping increases, we observed oscillatory responses with significant overshoots. Here are representative trials in the ML direction. Same as in the AP direction experiment, physical interaction was less stable as the magnitude of negative robotic damping increased. However, the range of robotic damping that human subjects can stably interact with was much smaller in the ML direction compared to the AP direction. We performed the arm stability experiments at 9 different arm postures around the neutral position in a 2D plane. All subjects participated in this experiment could achieve stable physical interaction with minimal overshoot when robotic damping was greater than -40 Newton-sec per meter in the AP direction and -20 Newton-sec per meter in the ML direction. Based on the results from the arm stability experiments, we designed the variable damping controller such that the lower bound of robotic damping is -20 Newton-sec per meter. With this constraint, the controller changed the damping component of a robotic impedance or admittance controller in real time based on user's intent of movement. User's intent of movement was defined as the multiplication of velocity and acceleration, which is a scaled measure of the change in kinetic energy of the human-robot system. So when this measure is positive, it implies that a human user intends to move. On the other hand, when it is negative, the user intends to stop the movement. Let me explain the controller with a simple example. This figure shows kinematics of a minimum jerk trajectory and the corresponding user's intent of movement and robotic damping. In the first half of the movement, the human user intends to initiate the movement and accelerate. The measure of user's intent of movement is positive, and the robotic damping is set in the negative range. Energy injection from the robot to the human user would enhance agility and assist movement. In the second half of the movement, the human user intends to decelerate and stop the movement. In this phase, the measure of user's intent of movement is negative, and the robotic damping is set in the positive range, which helps stabilization of the human-robot system. Here is a formal description of the variable damping controller. Robotic damping is calculated in real time using a dual-sided logistic function to smoothly vary in a predetermined range from negative to positive damping values. As the user intent measure, i.e. x dot times x double dot is getting higher, the robotic damping converges to the lower bound of the negative damping value, which helps agility. On the other hand, as the user intent is getting lower, the robotic damping converges to the higher bound of the positive damping value, which helps stabilization. The constants Kp and Kn are two tuning parameters of the variable damping controller. In order to accommodate speed variability across subjects, maximum and minimum user intent was first quantified for each subject, and these values were used to determine Kp and Kn. The sensitivity measure of S in the Kp and Kn equations further determines how quickly robotic damping varies in the predefined range. In order to evaluate the effectiveness of the variable damping controller, we first performed simple target reaching experiments using a robotic arm. The experiments involved 1D target reaching either in the AP direction or the ML direction. Based on the real-time visual feedback displaying current and target positions, subjects were instructed to reach the target as quickly as possible while minimizing overshoots. 3 different controllers were tested and compared. Specifically, fixed positive damping, fixed negative damping, and variable damping were tested. We evaluated the effects of the variable damping controller by quantifying agility, stability, and user effort during the target reaching tasks. We quantified the rise time for agility, percentage overshoot for stability, and interaction force for user effort. Our central hypothesis was that the variable damping controller would improve the trade-off between agility and stability, as well as decrease the user effort compared to fixed damping controllers. To test this hypothesis, we performed statistical analysis using one-way repeated measures Anova. We performed this test separately for each performance measure and for each movement direction with damping condition as the within subject factor. We also performed pairwise comparisons with Bonferroni corrections to evaluate statistical difference among 3 different controllers. 12 subject data was used in the statistical analysis. Here are a few sample results of a representative subject. With the fixed positive damping controller, subjects reached the target very stably without an overshoot, but the movement was rather slow. On the other hand, with the fixed negative damping controller, subjects reached the target very fast, but responses was less stable, evidenced by significant oscillations and overshoots. With the variable damping controller, subjects could reach the target very fast with minimal oscillations. The same trend was consistently observed in all other movement directions. And here I'm showing another example in the lateral direction. This figure shows sample results of kinematic responses, users' intent of movement, and the corresponding robotic damping. In the initial phase, movement intent was positive, meaning that the user tried to initiate movement and accelerate. In this phase, negative damping was imposed to enhance agility. In the later phase, movement intent was negative, meaning that the user tried to decelerate and stop the movement. In this phase, positive damping was imposed to enhance stability. Thus, the variable damping controller combines 2 distinct benefits of positive and negative damping controllers and improves the trade-off between agility and stability. Group average results of 12 subjects confirm the benefits of the variable damping controller in improving agility over fixed damping controllers. First, in all movement directions, the variable damping controller significantly shortened the rise time compared to the fixed positive damping controller. In fact, the rise time with the variable damping controller was as fast as that with the fixed negative damping controller. Group average results also confirm that the variable damping controller was much more stable than the fixed negative damping controller in all movement directions, evidenced by the significantly decreased percentage overshoot. Results with the variable damping controller was comparable to those with the fixed positive damping controller. The difference in the amount of percentage overshoot between the variable damping controller and the fixed positive damping controller was less than 3%. Last but not least, the variable damping controller significantly reduced user effort compared to any fixed damping controllers. This was evidenced by significantly reduced maximum interaction force and mean root mean square interaction force. After demonstrating the effectiveness of the proposed variable damping controller in the 1D study, we extended the validation to 2D planar reaching movement experiments. In this 2D study, target reaching trajectories were randomly generated by combining anterior-posterior and medial-lateral movements. Based on the real-time visual feedback displaying current and target positions, subjects were instructed to reach the target as fast as possible while minimizing overshoots, same as in the 1D study. Based on the previous 2D arm stability experimental results, we used different ranges of variable damping for the AP and ML directions. The magnitude of the lowest possible negative damping was 2 times greater in the AP direction than in the ML direction. Here is a summary of the 2D planar reaching study. First, subjects could stably complete the 2D planar target reaching task with the variable damping controller. Compared to the positive damping condition, the amount of overshoots was slightly increased, but the difference between the two control conditions was no more than 3 millimeters. While the level of stability was comparable in the two controller conditions, we observed significantly improved agility and reduced user effort in the variable damping controller condition. Maximum and mean speeds increased more than 30% and 10% respectively with the variable damping controller compared to the positive damping controller. Maximum and mean RMS interaction forces decreased by about 40% and 20% respectively with the variable damping controller. In summary, we demonstrated that the variable damping controller could improve the trade-off between performance and stability in physical humoral interaction by providing better agility without compromising stability and also reduce user effort. So, this controller can be used as an alternative scheme for traditional impedance and admittance controllers imposing fixed positive damping in many physical humoral interaction applications. Importantly, the proposed controller is general enough to be utilized in many applications in physical humoral interaction. We also tested the effectiveness of the variable damping controller in an ankle study, simulating ankle rehabilitation scenarios. In this ankle study, human users performed target-reaching ankle movement tasks in a multidimensional space spanning the sagittal and frontal planes. Consistent with the results in the arm study, we demonstrated the effectiveness of the variable damping controller in this ankle study. With the variable damping controller, subjects could significantly improve agility without compromising the stability and reduce user effort. Despite the promising results of the variable damping controller, future research is warranted in several areas. First, we believe that parameter tuning of the variable damping controller in a user-adaptive way will further improve its performance, which we will tackle in the next phase of this study. Next, we will extend the testing and evaluation of the controller in more realistic application scenarios. We will also design a variable stiffness controller and integrate that with the variable damping controller to realize a biomechanics-based variable impedance controller. I'd like to thank National Science Foundation for their generous support for this research. And I also would like to thank my students who have contributed to this study. Thanks for watching my presentation, and feel free to email me if you have any questions regarding this study.